It's really not, it's just not that good of a place to set it up in here, but it's, now you're like self-conscious the whole time. This one, Dominic, was here, didn't he? Right? Or was it? Oh, okay, okay. What else gets made? It's the other product. Keep going. Keep going. What happens next? What happens next? Yeah, good. What happens next? Well, always ask the question, right? What did you guys make? So it looks like everyone's got it. What did you guys make? An O with what charge? Positive. Okay, what do we call O with positive charges? Good leaving groups, right? So what flavor of leaving group did you guys make? What did you guys make? Right? Right? Okay, what flavor leaving group is this? That's a little bit tricky question, right? Want me to ask it a different way so that's obvious? Like, no, we're good, thank you. Okay, so what if I give you this instead? Okay, what's the product for that? I knew it the whole time. Knew I should get that close to you guys trying to steal markers. But don't work. Oh good, no trash can in here today either? Seems I want to move. I was outside now. Whatever you do. We what? We made a good leaving group, right? What's the leaving group? The things attached to the what? The oxygen there, right? So one side of the thing that's attached to the oxygen. You guys get what I'm saying? So instead of having a hydrogen there, what if I really change things up and just maybe put a carbon there instead? right? How would that change things? It wouldn't, right? In this case. Okay, so now what do we have? We have an oxygen with a positive charge, so it's a good leaving group. So we could make it leave. Well, what's going to leave? Well, either that chunk, right, or this whole thing leaves, right? You guys with me on this? Or I could cut it here, and then that whole chunk leaves, right? You guys with me on that one? Which one of those two will happen? Both, right? There's nothing really different about them. Got it? How is it going? Hang on just a second. How is it going to leave?
Gotta give it a reason to leave.
There's only two ways leaving groups leave, right? Someone kicks them out the door, or they just decide to leave on their own. You guys catch what I'm saying with this? If someone kicks them out the door, something attacks while something leaves, right? Got it? What type of mechanism is this? SN2, right? So now if something doesn't make it leave and it wants to leave on its own, then this happens. Right? What mechanism would that be? SN1. Which one of those will happen?
SN2.
Bold statement, Taylor.
I mean,
Why would you say something like that?
because SN2 is faster and there's no production of a carbocation.
What specific cation do we show forming here?
Primary carbon.
How many times are you guys going to see primary cations?
Barely.
None, right? You guys catch what I'm saying with this? It's important. Okay? So what's the preferred mechanism here? Well, we will follow the one in red there, right? So this makes a bond. Well, I just screwed all my colors up. Try this again, right? We make that, right? And what's the other product that we end up making? This. Good? You guys with me on that? Not going to happen. Formation of carbocation is slow. We make a primary carbocation. None of that stuff's going to happen. Do you guys see the problem though? What did we make here? An alcohol. What do we have around it? Strong acid. So what's going to happen next? Right? It's going to continue to react. Right? So oftentimes what you'll see, right, just to kind of clean all this up, if you have an ether and you put it in the presence of some hydrogen halide, HCl, HBr, HI, even HF to some degree, right? In the presence of excess HX there, right, it's just going to continue to react, right? It's going to break the ether apart, form the alkyl halides, right, and usually kick off water along the way, okay? So probably in some case like this, we would say that our products are this, right, plus this, right, and water gets formed along the way in some way. Good? Yes?
So, will there ever be an instance in where we perform an SN1 with this kind of?
Maybe, yeah, it depends on what you have there, right?
Okay.
So, but the point that I was getting across here is, right, so I gave you guys a new reaction, right? I gave you guys a new reaction that we hadn't seen before. I want you guys to start to use these things that we've been learning all along, right? You guys know that now when you see a strong acid, you're going to protonate an alcohol, an ether, these kind of things, right? Anytime you protonate an oxygen, we make a positive charge. It's a good leaving group, so we have to make it leave. And you only have two ways that you can make things leave, right? You can kick it out the door. Something else comes in and kicks it out the door, aka SN2, right? or it leaves by itself in SN1. We have a former carbocation or we don't. That's really all I'm saying. So when you're left with a choice like that, what should you do? Try both of them, right? Try both of them and see what it is. Do you guys catch what I'm saying with this? This is very important. What I'm saying is, some of you guys are going to still try and memorize this stuff. Careful with that, okay? Understanding how we get there and being able to kind of draw your own mechanism out of it, that's the important part, okay? When you come up with your own mechanisms is when you think about the steps that we've been doing. Still this semester, I haven't shown you guys anything new yet, right? It's all the same stuff we had before, just kind of applied to different looking things, okay? All right. So now we got to think here a little bit, right? Yes. Thinking. Why does it keep popping? Sure, that seems good. So we'll fill in the blanks there. We go from one end to the other. You got the right idea, just be careful.
For the, this part or the bottom?
The part that you have to mark there.
Okay.
You have, like I said, you have the exact right idea, just count, just make sure that you're carbons with that.
Gotcha.
This? What is this? No, negative carbon, negative carbon, actually not. You have to be very careful, right? What you had there before, it's a really powerful base. As soon as you put a really powerful base with an alcohol, what's going to happen first? Acids, right? Good. So now what? How do we get that part in there? No, I think you do. I think it's right there. You can almost taste the answer. Bitter in your mouth. Tastes like organic chemistry. Good. That's okay. No, all right, keep going. Remember, what we see over here on this side, right, we see an asymmetric ether, right? We see an asymmetric ether, an ether that has different R groups on both sides of it. There's only one way we really know how to make an asymmetric ether, that's our Williamson ether synthesis. Right. Right? Okay. I remember our Williamson ether synthesis, the first thing we do is we deprotonate the alcohol to make the alkoxide there, the O with the minus charge. Right? So we add in some sodium hydride. And then the second thing we do is we add in the alkyl halide, right? Good? So we deprotonate to make a decent nucleophile, and then we add in something that it can do an SN2 reaction on. Good? Yep.
Is there another way we could have done like that bottom part?
Is there another way?
Yes.
In what sense?
Like, I was,
Do you want me to come judge harshly? Is that what you're
yes.
asking?
Because
Okay.
I didn't know if that,
How do you add that? So let's see what it says. You have to add a carbon. You have to add carbons to it in some way.
okay, so then, because I don't know, I thought that would have been like two sterically hydrogenases, or.
So that's an interesting thought, right? Yeah. So I like the way you're thinking with that, but I'm not trying to trick you guys in that sense here.
Okay.
Right. Yeah. Cool. Now you guys ready to think? Do you guys want to get mad? Or do you guys just like numb to it all now? You're like, nah, Dr. H, you've already crushed everything that I believe in. It's good. Just go ahead and hit me with more of it, right? I want you guys to think now, all right? Really think. Yeah. Be careful. I tell you I'm trying to trick you. You can't say I'm trying to trick you, right? What's that? Hmm. What do you mean? Yeah, sure. I mean, that's why I have to run the two, right? Those are two separate reactions that are happening.
But yeah, no, like in accordance to like this second problem. Okay. I will do it and then I'll show you.
Okay. Yeah, I don't think I'm quite understanding what you're asking.
I don't even think I understood what I was asking.
I don't think Ian understood what you're asking.
Ian doesn't understand a lot of things.
Oh, man, what is with this? You need so much hate for that, dude.
I'm not that nice of a person.
When do you go back to the quarantine? You guys all self-conscious now? I know he's trying to trick us. So I know that acid-base reactions aren't magically going to happen, right? No, that's not it, right? So nothing different there. Do we have a strong acid? Yes, right? Do we have some kind of oxygen-containing functional group? Yeah, probably wouldn't be a bad idea to start by protonating that oxygen group there, right? Good, right? Nothing unusual so far. So what's supposed to happen next? Right, we have a good leaving group, and so we need to give it a reason to leave, right? What's up, Taylor?
Oh, I was gonna say, like, wouldn't the bromine attack the carbon right next to the
Mm-hmm.
and kick it off and force it?
But that's the question, right? Because if you caught Taylor subtle there, she's like, you attack the carbon, right? The question is what? Which carbon? In the previous example, neither of those carbons were any different, right? They're both primary carbons, yada, yada, yada. What's different here? Now we've got not a secondary, but we've got this alkene carbon, right? A carbon in an alkene bond. We would call that a vinyl carbon, a vinylic, like V-I-N-Y-L, and a vinylic carbon. And then on the other end, right, so we have our vinylic carbon here, right, in blue, and here in red we have what? It's got a regular old boring snooze of a primary carbon, right? So which of those two carbons is the bromine going to hit? The one that we've never seen any chemistry with before in blue? Or the one that we've seen do chemistry all the time in red? Which one do you think, guys? Right? Okay. So here are products at the end of the day are that blue running out of space and that. All right, and it stops there. That alcohol doesn't react again. Huh, right? Interesting. So, somebody asked me the good question.
Why?
Why indeed, right? So, that's what we're going to talk about next, okay? We're going to talk about why we see a difference in reactivity between the blue carbon there and the red carbon there, right? We're going to talk about what makes these specific types of carbons behave a little bit differently. Although you guys already know, right? Because what's every good answer in chemistry come down to? Ferrics or electronics, got it? So you guys have a 50-50 shot. Which one do you think it is?
Electronic.
There you go, good answer, okay? Now the question then would be, well, why? How? What's going on? Okay? And so that's going to be the next, this is going to be the first kind of new stuff that we encounter. We're going to talk about a little bit about what we call conjugated systems, right? And we're going to talk then for about, I don't know, I think it takes like 2 or 3 chapters in the book to talk about aromatic systems. We're going to talk about chemistry and how they behave and all this kind of stuff with it. At the end of the day, there's going to be 2. Yeah, basically 2 mechanisms that we learn out of 5,000 reactions, okay? So we're going to learn a new type of SN reaction, right? So we'll add it to our SN1 and SN2. And it's actually a very useful SN reaction, but we won't use it all that much here, right? And I'll come up with a bull-crap reason why that is. And you guys go, yeah, that sounds good, right? Right? And then we're going to learn another type of reaction that we will end up using all the time. Okay, so it's a little bit of disparity here in terms of how we present the material in the undergraduate course, right? But two new mechanisms coming your guys' way. Okay, and that'll help explain why we see a difference here between the blue and the red. Okay, because for the moment, if you remember what I told you guys all in the first semester, we said don't do anything on aromatic rings, right? Don't do it, don't touch them, don't change them, they're just there, look at them, admire their beauty and symmetry, and then move on with life, right? So now we're going to actually kind of learn how to start to do some of those things there, okay? But before we get to the good stuff, we got to go back and do more things that we already learned in OChem 1, okay? So, all right, I actually have to bring notes for this stuff because there's a lot of information, and I forget. Okay, so, chapter 15, right? Pretty sure. Let me just double check. No, 16. Sorry. So chapter 16. So, conjugated systems. All right? I gotta give you guys some easy ones every once in a while. Now you guys are like super stressed about it. I believe it makes a bromine. Oh. You guys like Jolly Ranchers? Yeah. So if I start bringing those for you guys when you do good.
Incentive.
Yeah. I'll just think about it. Order some stuff on Amazon. So I was like, yeah, I should get those. But see, I'm very picky. This is really important. You guys have to know about my preference for Jolly Ranchers, so you have to listen to me. Okay? Like grape sucks, right? Yeah. Look, what? No, look. When you teach your own class, you can say whatever you want. Water, the cherry ones. I don't like those so much because they like turn your whole like mouth blue, right? Yeah. So it looks like you were like chewing on your pen and like exploding. Grape sucks. Apple's overrated.
Watermelon.
Sucks.
Watermelon sucks.
Yeah. Like I said, it's like cherry, and then everything else is meh. But it's good, right? We have a nice, diverse, enjoyment of flavors in here, so we don't all have to fight for whichever flavors it is, right? So I'll have to go order some stuff for you.
That would be great, thanks.
Huh?
That would be great. I would appreciate it.
Good. We'll get it done. Don't say anything, because they were like, so we have to like socially distance from Jolly Rancher. Get my slingshot, like in the back, Taylor, get in. Anyway, though, how many products do we get out of this? 3. Ooh. Let's see if you guys can think of what all 3 of them are, right? A very great Jolly Rancher set of answers there. Remember, as soon as I show you guys what the 3 are, you're going to go, man, cheese. What's the intermediate? A carbocation. Every time you make a carbocation, what happens with our product? You end up forming what do we end up forming? A racemic mixture, remember? So if you form a chiral center, you're going to form the wedge and the dash, the R and the S, right? Don't forget about that. So we've got an asymmetric, right? We've got an asymmetric, I'm going to put the same colors in that, that's not what I wanted to do. Let's try this one more time. Okay, so we've got 2 unequal sets of carbons there, right? And so we can end up putting a chlorine on either one of those, right? We can end up putting it there. And we can end up putting it there, right? Remember the one in pink chiral center, so you just end up making 3 products, right? But it's cool, right? If you guys got the 2 there, just the first ones that I showed you guys, that's great too, right? But just keep in mind, right, whenever we're making a carbocation, that's one of these, another key things to remember. Carbocation intermediate, racemic mixture, RNS, all that kind of stuff, okay? So, we learned a lot about the chemistry of these alkenes, right? This is what's known as an isolated alkene, okay? So, it's just an alkene that's out on its own. Let's just do this here. Okay? Now we've got an alkene, right? We've got a double bond, single bond, double bond. Right? You guys see what I'm talking about there? Double bond, single bond, double bond. Right? They're right next door to each other. Okay? This is what's known as a conjugated system. Okay? Now, it's not just limited to 2, okay? It's not just limited to 2. And any amount of double bonds, right? Double bond, single bond, double bond, single bond, double bond, single bond, right? That's a conjugated system. If you guys look it up, if you guys look up retinol, right? And beta carotene, right, the stuff that they say is good for your eyes and all that kind of stuff. You'll see it's this big, huge conjugated alkyl chain there, okay? Conjugated systems end up bringing in some pretty interesting spectroscopic properties, right? The bigger the conjugated system, the more likely it is to absorb light, and depending on what you have around it, we can start to absorb things in the visible spectrum, right? So if you look up lycopene, which is the thing that gives red fruits and vegetables their red color, you'll see it's this massive conjugated system also, okay? So a lot of the colored compounds that we'll end up seeing is because we have these kind of conjugated systems kind of showing up in there, right? And later on in the semester, if the class learns how to read bottles, afternoon sec, I don't know, maybe the morning section ended up with that too, I don't know, we'll see what happens. But we'll end up making a compound that changes from red to yellow to blue, just based off of different the different energetic levels of the conjugated systems that we make. Okay? So, but very, very, very common idea there, right? These conjugated systems are everywhere. Okay, the green color in plants, or even the yellows and the reds, and all these kind of things, all come from these kind of conjugated sets of systems there. Okay. All right. Nice. Great. Now we can explain somewhat how colors work to a degree. Now I want you guys to think. Right? Now I'm going to be kind of lying to you guys for the moment, and we'll come back and clarify what the lie is. Okay? And I'm going to tell you guys that there's 2 products that come out of this. Okay? And what I'm not saying is that, well, I react one of the alkenes and then I magically react the other, right? Those would end up making the same product. There's 2 unique products that come out of this. See what you guys can come up with. excess of that, but just let's assume we have one equivalent of that. Pretty good. Good. Don't forget, you put that from here. So those are the same compounds. Yeah. Right, you've got an alkene at the end, you've got a chlorine on the 2 carbon, right? Mm-hmm. Yeah. So that is one of the products, but that is, let's say, an identical product, right? What do we have to stop and do when we see it? Stop next door and look if we can do that. You're almost at the right idea. Not a hydride shift, but you've got a carbocation here, and what's next door? So what can you do? There it is, right? Do that. My eyes are burning. Oh, jeez. Alright, so this is going to react with that. I agree with that. But you're never, like I said, I'm not, all joking aside, right? I'm not going to give you something out of the blue like that, right? So you're not going to form a primary. So one of these 2 carbons is going to have that positive charge, right? So you put on the more substituted one. Okay? It's good. Don't forget your. Erase the stuff that you have there. Yeah, and within everything else. Okay. Draw, so forget what you have in your brain at the moment and draw exactly what you have there with your arrows. Okay. What are you showing with that arrow right here? Okay, so show me that. Okay. Draw me that product. Okay. Where are you taking electrons away from? That carbon, so where's the positive charge now? There you go. Good. Interesting thought. So hang on to that, right? That might happen if we have an excess of HCl. So let's just assume we have one. So it's I like the way you're thinking with that, right? I won't say you might necessarily be wrong, but just work with one. Erase that big arrow for me there. Yeah. Draw that product right there. So you're sending electrons to something that has a positive, and so has a positive at the end of it? No.
Oh, I just wrote wrong.
How did that positive charge get there? It didn't add or remove any bonds from it. Where did you take electrons away from? Aha, got it. I like this, I don't like that. Draw that product right there. You drew, this is the right, this is, don't put that positive charge there.
Oh, so it's always a distance here.
No, the positive charge is going to be where you took electrons away from. Right? Where did you take electrons away from? Yeah, probably. I don't know what you're really asking.
I don't know if I'm done or if I'm missing something.
Oh, we're never done, right? Life would be boring if we were done. Good? We got this, yes? We pick one of our alkenes, it doesn't matter which one. We make it swing open. We grab the hydrogen, right? So we add one of our hydrogens over here, right? Positive charge there. Everything's nice, everything's easy. Life is simple. Right? Did I catch somebody on this one? Don't forget, every time you have a carbocation, right? To zoom in way too much, right? So technically, remember, this is a chiral center, so you have your RMS there too, right? Didn't catch anybody with it. Okay, you guys all got that. All right, good? We got this part? Everybody with me so far? Okay? I want you guys to stop and I want you guys to think. Okay? Right? We've got a carbocation. Every time you guys have a carbocation, what do you need to do? Stop and think. You have to. Because otherwise you're just going to get in the habit of the carbocation and you like keep on speeding on to the answer, right? Okay? Always look next door. Because when you have a carbocation, what do you need to do? You need to find a way to stabilize it. Now, in the last semester, we talked a lot about our shifts, right? Alkyl shifts and hydride shifts. Yes? And we said that we can shift from a less stable to a more stable. Right? So we can shift from like secondary to tertiary. Right? Do we have any tertiary carbons here? No. So are we going to see any hydride shifts? No. Are we going to see any alkyl shifts? No. How and what is the best way to stabilize any charge, though? Resonance. You know that thing that you guys kept missing on exams and stuff? That you guys thought would go away? Right? I've got a letter on, I think I might have told you guys this story last semester too, but it doesn't matter. I have to tell it to you again. And you guys have to sit there and listen to it, because that's what you guys paid for, right? So I got a letter from one of my students. It's sitting on the, behind my computer on my desk. It says, Dr. H, you were the bestest ever professor. No, it says something like that. That's not the important part. Right? The important, well, I mean, it is, but the second part of the letter says, you were right. We use resonance structures an awful lot in OChem too. You guys get the point? So you don't have to listen to me. I can show you the letter. I didn't just make this up and like write it to myself. Watch this. Don't believe this story. Right? You got to remember it. You got to start looking for resonance structures, especially as we move into this aromatic chapter and as we move forward from this. Pretty much I think every mechanism that we learn from this part out is going to have some form of resonance structure with it. Okay? You have to do it. You have to. Dr. H, I don't understand it. I suck at it. Get better at it. Dr. H, my stomach hurts. Learn resonance, okay? Right? Right? What I'm saying, you have to know how to do it. You have to. Okay? You have to know how to move positive charges. You have to know how to move negative charges. You have to be able to draw the arrows. You have to be able to draw the resonance structures. You have to be able to assess whether resonance structures are equivalent or whether they are inequivalent. Okay? Am I putting a lot of burden on your guys' shoulders? Yes. Right? But you have to know it. There's no, like, I'm not holding some secret knowledge away from you guys on this. You just have to do it. Okay? You have to get better at it. You just have to try it. You have to keep practicing. You have to go back, refresh, watch some videos, whatever you guys need to do. You're going to have to start to learn how to draw resonance structures. Okay? Did I get my point? Was everyone with me on this? Please, please, please. Okay. All right. So next door, right? There is our positive charge. Next door we see a pi bond. So we can draw a nice, pretty resonance structure. Okay? Good. Somebody observe for me. Yeah.
The primary.
Huh. So did I make a mistake? Thank you. All right. But that's right. So what did we do? We ended up drawing a resonance structure. Is there anything invalid with the resonance structure that we drew? No, right? We had a positive charge. We had a pi bond next door. We could move that over, right? But we did end up creating a primary carbocation, right? Is this really a primary carbocation?
No.
No. What do we know about resonance structures? Resonance structures are instantaneous, right? Both of those exist at the same time. Not necessarily 50-50, right? But both of them exist at the same time. So is it really a primary carbocation? No. Is it really a secondary carbocation? No. Is it somewhere in between? Yes. Okay. So remember, when you come up with a resonance structure like this, you have to ask yourself the question, what is the best resonance structure? What's the most stable? Which one of these is going to react? Usually the answer is going to be both of them react, right? You guys see if we follow along the top there, we already made one of those react. So along the bottom here, right? We come up with this product here. Good? So, now we have the other question. Let me bring this back in here, just for argument's sake, so we can all take a peek at what's happening. Okay. Well, let's do this in red instead. And we'll do this here in green. And now you guys have to go back and erase everything in your notes. Ah, damn it, right? This is different colors. Okay. So we have two products. Good? We have the one that we made in red, and we have the path that we followed in green. Are those both unique products? Yes, they are. Which one's going to happen fastest? The one in green, and red, sorry, yeah, red, sorry. I thought I had drawn it in green, right? The one in red. Why?
Because it doesn't have a shift.
There's no shift. How many steps does it take? Well, 2, right? We have to do the HCl attack and then the attack of the chloride, right? You guys understand that? So 2 steps, okay? What if we follow the green route? How many steps do we have there? 3. What's faster, 2 or 3? 2, got it, okay, right? No trick question there, okay? So what we have here is a difference between our kinetic product and our thermodynamic product, okay? Now, if you guys remember from Gen Chem 2, kinetics. What do they teach you at this school? They teach us how to steal food from the cafeteria. I need more Captain Crunch. Let's go on a raid. So, right, was it him? Is that what your question? Ian, you screwed it up for all of us. Jeez. Right? So, remember when we're talking about kinetics, it's just how fast does something go, right? Remember when we talk about kinetics in Gen Chem, we were talking about rate equations, right? And is it a first or second or third order, right? All these kind of things that go with it, right? Right, rate equals K times the concentration of the reactants, right? That kind of stuff. Make a little bit of sense? Kind of remember that a little bit there, right? What we're talking about here with kinetics, we're just saying this is the fastest product, the fastest reaction that happens. That's all we're talking about here, okay? The thermodynamic, right? And you guys talked a lot about thermodynamics in Gen Chem also. Right? The thermodynamics just talks about which product is the most stable. Okay? Now, in a case like this, we have separate kinetic and thermodynamic products. Okay? But for a lot of the reactions we've been doing so far, our kinetic and thermodynamic products are the same. Okay? I'm not saying they necessarily always have to be different things, okay? But we see a distinction here, especially when we deal with these conjugated 1,4 additions, okay? Conjugated 1,4 additions. Now what am I talking about with a 1,4 addition? Well, we have 1, 2, 3, 4, right? We have 1, 2 additions, which is what you guys have been doing all along. And we have 1, 4 additions, which is what you guys have been doing for 5 minutes, okay? Right? That's the new stuff that we just did. You guys with me on that? Does that make sense? 1, 2 versus 1, 4? No? Yes, maybe? A little bit? All right, resounding indifference from the audience. We're putting pen to paper, right? This is our fastest thing, kinetic. And here is our thermodynamic. Somebody asked me a good question.
What's the difference?
I already answered that. It's a good question. No, right? So what's the difference? Okay, it's a good question. So remember when we're talking about kinetic, it's basically what takes the least steps to happen. Okay? The simplest route to get from part A to part B, from the products to the reactors. Okay? Be like me asking you, do you want to run 2 miles for an A or 3 miles for an A? Okay? You guys would say, just give me a B, right? Right? You guys would say, I'd rather just run the 2 miles, right? It's simpler, it's easier to get to the end goal at the same quicker, right? That's what we mean by kinetic. The thermodynamic is which is more stable, okay? Which one makes the better bonds might be a way of thinking about this, right? Yeah.
When, like, thinking about which product gets made more, is whether it's kinetically or thermodynamically quicker.
Fantastic question. So hang on to that thought for just a second. I'll answer that in just a minute, okay? Very, very good question. How do we know? How can we select? How can we control one versus the other? Yeah. So I have a question for you guys. I am claiming that that product in green there at the bottom is thermodynamically stable. That molecule that we made is more stable than the one that's up there in blue. Why? I haven't heard from Sophia today. Go ahead.
Because you have the resonance structure, so it's technically not a full positive for the carbocation because it goes between the two.
So that's an interesting thought, but let me counter with this. We still have a resonance structure in the red pathway there, right? Remember that it's instant. Both of those exist. So it's an interesting thought that you have there, but don't forget, just because I didn't show it to continue on the red doesn't mean that doesn't happen.
I haven't seen that.
Okay.
Because of the terminal alkene.
What do you mean?
I don't know.
So that's a, I hate to call it a guess, right? But there's something that stuck in Ian's brain there. It said, wait a minute, I remember talking about terminal alkenes. How do we determine stability of alkenes? What do we have to take a look at?
What's around it?
The more stuff you have around them, the more stable they are. You guys remember talking about tetra versus tri versus di versus mono substituted alkenes? The more crud you can stick around an alkene, the happier it is. Which one of those alkenes is more crud stuck around it? The second one at the bottom, right? It's got 2 carbons on both ends. The one on top only has 1 of them. Okay? The one on the bottom is a happier alkene. It has the better bonds, right? If we want to make a statement like that. Good. Cool. So I think that's a pretty good place to stop, right? Need you guys to go brush up on your resonance structures. Be very, very useful for you guys to do over the weekend there, right? See if we can remember how to draw them and move charges around and that kind of stuff. And then when we come back on Monday, I'll answer Anna's question there about how do we pick one versus the other, right? How can we be maybe selective about it, right? So which is kind of the theme of the semester there, okay? Awesome. I will see you guys on Monday, and we'll pick it up from there. And expect at least a quiz next week, right?